How's it going, everybody? And why is that doing that again? Alright, sorry about that. How's it going, everybody? In this video, we are going to be discussing how OSPF works. We're going to be getting into a little bit of the meat and taters of how the protocol does its thing. So we're going to walk through how that actually works, and then from there, we're going to go through all the detail first. There's like a step-by-step breakdown for OSPF. So without any further ado, let's go ahead and dive into it. Okay, so how OSPF works. Step 1, you have to discover neighbors and exchange routing info. Step 2 is you have to choose the best path via the shortest path first process, or SPF. Step 3 is neighbor and topology table maintenance. So the first step in this process is use hello package to discover neighbors on interface enabled to run OSPF. Remember that OSPF has its own protocol number, and that is 89. And it uses multicast to 224.0.0.5 or 6 or unicast in order to form adjacencies. Now we'll talk a little bit about how .5 and .6 are a little bit different, but essentially .5, if I remember correctly, I'd have to go through and look for... Yes, okay. I knew it was down here somewhere, but 224.0.0.5 is all SPF routers, so just normal OSPF enabled speakers. And 224.0.0.6 is all designated routers, or DRs, and we'll talk about what the difference between a DR, a backup DR, and then a non-DR router are in a little while. So 224.0.0.5 or 6 depending on the scenario. Now, the hello packet contains attributes that neighbors must agree on to form adjacency. You can form a neighbor relationship but not form an adjacency. Like, huh? How does that work? But I'll get to that in just a minute. If you form an adjacency, you can also form a neighbor relationship. Once adjacency is negotiated, the link state database, or LSDB, is exchanged. Negotiating OSPF adjacencies. Adjacency occurs when connected neighbors agree on unique and common attributes. Not all OSPF neighbors actually form adjacencies. Most OSPF configuration problems happen at this stage. So what do I mean by not all OSPF neighbors actually form adjacency? Well, there's two different scenarios that come into play. I'll grab the first one because it's the default process. You have the broadcast network type and you have the point-to-point network type. By default, broadcast is the default mechanism on Ethernet interfaces. So anything that's Ethernet, gigabit, 10 gigabit, megabit, all those interfaces are Ethernet interfaces. Therefore, they will default to broadcast because Ethernet is a broadcast media. Therefore, it is assumed that you are looking to talk to more than one endpoint at any given time, even if there's only two devices on a particular segment, like a /30 or /31 subnet mask. And what this means is when you're forming adjacencies and you're sending out your hellos, and we'll talk a little bit about how that process works. When you're sending out hellos back and forth, what's going to end up happening is on a broadcast network segment is a designated router election is going to happen. So let's assume that there's two routers to start with. If there's two routers, one of those devices is going to become the designated router, and then the other router, not the designated router, will become the backup designated router. And this is based off of the priority. So when we talk about how this comes into play, that's going to be the key. That's the first key feature, the DR BDR election process. Let's assume that there's three routers on a segment. So you've got three routers all on the same LAN segment. What happens then? Well, you have your DR election, you have your BDR election. Once those two are done, then you have all of your other non-DR or DR other, as it's referred to. So in that particular situation, whoever is the DR is going to be your .6 IP address in the 224.0.0.6. The purpose of the designated router is, that of like a designated driver. You go out to have a good time, and you designate somebody that's not going to do anything that they shouldn't be doing, right? Not drinking. Well, in this case here, everybody is going to send all of their information that they have about OSPF, all of their LSAs, their entire leak state database. Everything's going to be sent to the designated router. The designated router's job is to then disseminate or hand out that information to all of the other OSPF enabled devices. Now here's the caveat. When you are looking at that, the way that the DR process comes into play and the election and all other stuff goes on, the assumption is, and I use the term assumption because of the way that the process works, is that if I can reach the DR and the DR can reach them, it is implicit that I can also reach them. So that's, some people get hung up on like, well, why do we need a DR? Well, you have that election process only if you use the broadcast network type. Rob, can you change it? Yes, you can. You can change it by going to the interface level and typing in IP OSPF network type point to point. Now, when you do that, you remove the DR BDR election process. Okay, fairly simple to understand, right? Now, let me ask another question. Why do we need the DR? What's its, other than the description you just gave, why else would you use that? Well, there's a specific LSA, link state advertisement, that is tied to the DR that comes into play with that. And that is going to be the type 2 LSA, which is going to be your DR LSA. The DR LSA, it goes back to what I just mentioned a moment ago. If I can reach the DR and the DR can reach the other devices, it's implied that I can also reach those other devices. The idea is that if I can reach it, so can they, and he can reach them, so can I. The idea here is reachability. Now, if you don't want to deal with that, and a lot of customers don't, there's a lot of capabilities that require you to remove or to move to the point-to-point network type, and we're going to talk about that, where that's going to come into play, like OSPF fast reroute, FRR, things like that that'll come into play. Those are the specific things that need to come into play. So now, specifically when it comes down to this, when you form an adjacency on a broadcast segment, you are only going to form an adjacency with the DR. You are going to send hellos and receive hellos even from the other OSPF speakers on your segment, even if you don't form an adjacency with them. There's a multi-step process to the adjacency forming process, and if you are going to find neighbors, so it says right here, you can form a neighbor relationship but not form an adjacency. A neighbor relationship means that you see them, but you don't actually exchange any routing information with them. The only time you exchange routing information is if you form an adjacency. So neighbor relationship is the very first thing. It's like, think of it, a loose analogy to this is somebody new moves into your apartment complex, your neighborhood, whatever case might be, a new coworker, first day on the job, and the manager or whatever, or that you decide to like be neighborly and come out and say, hey, I'm Rob, nice to meet you, welcome to the neighborhood, that type of stuff. Well, what ends up happening is the neighbor is literally just that. You're just doing initial introduction. And the way that you're going to know this is based off of the output from the show IP OSPF neighbor command, and you'll get to what they call two-way. Two-way state simply means that I can see you, you can see me. And how do you know you can see me? Because whenever I say hi to you, I will send you my router ID. My router ID is my unique ID in the network. If I send you my router ID and a hello, you receive that hello, and then you're going to put your router ID in a hello and send it to me. What's cool about that is when you send me your hello, you're going to put my router ID in your update to let me know I can see you. And that's how it goes back and forth. When you do that, you have reached two-way state, which means I can see you, you can see me. It's like you're passing in the hallway. You can see that person, guy or gal, whatever it might be, and you make eye contact. It's not that you see them and they're just passively ignoring you, talking to somebody else or what have you. you actively lock eyes, and some kind of dudes will, give you a silent nod down, and it's just a quick acknowledgement. We see you, you see me, we nod, you nod back. It's a non-verbal communication. Or in this case here, we're communicating back and forth. You can see me, I can see you, everything's good. That doesn't mean we know each other, right? I know he's there, stuff like that. So, it's kind of funny. My next door neighbor, I've lived next to him for quite some time, and he'll be doing whatever, and he'll be out and about, I'll be out and about, and all we literally do is when we see each other, we point. That's it. We don't have to wave. That's like our wave. So it's just one of those things where you see me, I see you, we're good to go, and you can have an entire conversation without even saying a word. Kind of funny actually how guys are like that. So that's essentially what that is. So that's a neighbor relationship. You see them. You show IP OSPF neighbor, you're going to see it show up in your neighbor table. However, you're going to see it set to two-way, 2-WAY is how it's going to show up. Now, for neighbors that you are the DR or the BDR, assuming you have a four nodes on a linked local or on a LAN segment, you're going to form an adjacency with the DR and the BDR. The third one, being the other router that is not the DR, you're going to stop at two-way. Now, what happens when you're at that point? What's going to end up happening at that point is you're going to go to two-way, but if something happens with the DR or the BDR, the other router will start to come online, and he'll form an adjacency when there's a problem. So if for whatever reason the DR goes down, whatever, it doesn't matter. If the DR goes down, then you'll automatically form an adjacency with the other router, because the the backup designated router, the BDR, he will automatically go and take over the DR process. And then the other router that wasn't running the DR process at all, for DR or BDR, he will then become the backup designated router. So that's essentially how that comes into play. The thing about the DR process, and we'll get more into that and how it works a little bit later and actually adjust who the DR is, but what will end up happening is the DR process is not preemptive. What that means is if the DR has been elected and is online doing its thing, and then for whatever reason it ends up going away, he goes offline. Well, what's going to end up happening is he comes back online, somebody else took the DR process, somebody else took the BDR process, and now you come back online as just a DR other, assuming you haven't done something to basically force yourself to become the DR. So if you're not doing anything to make yourself the DR, you will come back as a DR other and only go to two-way. So it's not one of those things like a BGP route reflector where you're always going to be a route reflector. You're not always going to be a DR. But we'll talk more about that in detail later when we get into the background. So again, if you form if you form a neighbor relationship but not form an adjacency, if you form an adjacency, you also form a neighbor relationship. So they're not one for one. Once adjacency is negotiated, the link state database is exchanged. Negotiating the OSPF adjacency itself is actually relatively straightforward. Again, adjacencies occurs when connected neighbors agree on unique and common attributes. And again, not all OSPF neighbors actually form adjacencies. So, unique adjacency attributes. For one, the router ID. Again, this is a node ID in the link state graph, chosen based off of one of three different mechanisms. Manual config, so you type in underneath the OSPF process, router ID 1.1.1.1, for example. Then the highest active loopback IP, so if you have a loopback address, then whatever that IP address is, that will become the router ID. If you don't have any loopback addresses and you haven't manually configured it, the highest active interface IP will become your router ID. Now, there are situations where you can manipulate them. So if you've used a loopback address and then you decide to go manual config will take over. However, here's the funny part. When you do the router ID, this is going to be once it's been set, the only way to unset it and change it is to bounce the adjacency. So if you're in a production environment, you're not going to be wanting to manipulate OSPF adjacencies on a regular basis, right? You want to keep your routing consistent. So in situations like that, the thing to keep in the back of your mind is I don't want to monkey with this. Once I have the router ID set, I'm going to keep it where it's at. So it's usually why it's a good thing to get in the habit of manually setting your router IDs when you develop your configuration, so you don't have to go out and mess around with it down the road. So just keep that in the back of your mind. There's a question. Do you have to have a router ID? Yes, you have to have a router ID. Now, the cool thing about the router ID itself is it's an identifier. Doesn't have to be an actual routable IP address. Now, it'll be an actual IPv4 address, but it doesn't have to be a 10.1.1.1. It could be any address for that matter. Now, I did say here node ID and a link state graph. So let me talk a little bit about that real quick, just so that everybody's on the same page here. I think I mentioned it up here. Okay, so designed to route to the node that owns the attribute that is the prefix. What does that mean exactly? Well, let me do a little bit of quick whiteboarding for you to explain what it is that I mean by this. And once this was explained to me, it really made OSPF click. So let me go ahead and scroll down here again to what that means. So it's actually a very simple concept. So I'm going to draw out a couple of devices. So I'm going to draw R1, I'll draw out R2, I'll draw out R3, I'll draw out R4. Okay, so these guys are all connected to each other, right? And let me go bring these together, and then let me do this one here. So here's how this is going to work. So R4, R3, and R1, all the odd numbered routers have a LAN segment attached to them. So let's say this is 1, 1, 1, 1, this is 2, 2, 2, 2, this is 3, 3, 3, 3, this is 4, 4, 4, 4. Simple enough, right? So the numbers are the router IDs for each device. Now what's going to end up happening is, let's assume that for every segment here we got this is 1.2, this is 2.3, this is 2.4, this is 3.4 here. Simple enough? Good. So what's going to end up happening is, if I advertise this guy, so I'll type in 10.1.1.0/24, then I've got, 10.3.3.0/24, and then over here I've got 10.4.4.0/24. What will end up happening when you look at this is you have the concept of links, and then you have the concept of nodes. The idea here is that if I have a link and node, I am going to be looking for the information that's coming from the node, not the link. And why do I not care about the link? Well, the reason why I don't care about the link is because in most cases, I'm not going to be trying to route to a link on a device. So if I'm on R1, I'm more than likely not going to try to route myself to the interface that owns 10.2.4.4. That's probably not going to be the case. What I will probably try to route to is 4.4.4.4. It's more than likely going to be a unique address. The thing that you don't want to do is you don't want to use this nomenclature, 2222, 33333. You don't want to use that type of addressing scheme for your router IDs. You're going to want to grab a RFC 1918, so RFC 1918 address, and you're going to want to grab a specific subnet. And that subnet is going to be the IP address that you assign for your router IDs. What's going to end up happening is this. I'm not going to route towards the link. That doesn't make any sense. What I am going to try to route to is the node. Now here's the interesting thing about that. The way that I analogize this is, I'll give you the technical, then I'll give you the analogy. The technical piece is, if I'm on R1, I am going to figure out the best path to the router ID of 4.4.4.4, because 4.4.4.4 is advertising 10.4.4.0/24. That's the technical breakdown. The analogy to it is this. I want to go buy a new pair of pants. So what I'm going to do is I'm going to, and there's plenty of stores in the area that I live in that sell pants. Well, I'm looking for a specific type of pants. Let's say I'm looking for a new pair of ski pants because I like to go skiing in the winter. Got to have something to do in the winter to keep myself active. Well, what I'm going to do is I'm going to go pull up my phone. I'm going to go like stores near me that sell ski pants. So it's going to say, well, Walmart sells ski pants. You know, sometimes they're referred to as snow pants, stuff like that. Same difference. So what I'm going to do is I'm going to look that up. And let's say, for example, there's a store that's not too far from me. It's called Les Moise. So I'm active outdoors during the wintertime, skiing. I got a kid that snowboards. And so this is a ski and snowboard shop, right? So ski and snowboard, right? That stuff you guys really don't care about. The part that you do care about is this. Well, Les Moise happens to sell ski pants. Well, so what I do is this. I don't go looking for the ski pants specifically, right? I'm not trying to get to the ski pants. My goal, it's my end goal, but it's not what I'm not literally getting in my car and driving to the ski pants. My goal is to drive to the store, Les Moise. Les Moise has ski pants in the store. So therefore, if I get myself to the store, Les Moise, then I can get out of my car, go walk in the store, walk to wherever the ski pants happen to be in the store, and go, oh, okay. Then I look at all the different brands they have, colors, shape, size, all the good stuff that goes along with that. I find this pair of ski pants that I like. I look at the price tag, try not to freak out because they're usually on the more expensive side. And then I go find a dressing room because I want to try them on. So I'm not a big guy, 5'10", 180. So I go into the dressing room, I try them on, like, yes, they work. So normally I'll bring my ski boots with just so I can try them on and make sure they're going to work the way I expect them to. And then I'm a happy camper. I go to the cashier, I pay my bill, and away I go. Well, the whole point of that is this. This right here is the node, right? Remember, we're trying to route to the node. This and this is the link. This is what's attached to the device. So, long story short, if I route to the node owns the prefix because it's physically attached to it. So if I route to the node that advertises the prefix, therefore, by routing to the node, I have also reached the prefix. Now, technically speaking, it's another device, right? I have to route through the router, or route through the switch, or route through the access point. In most cases, the access point is not going to be a router, but I digress. You're going to route through the infrastructure device, router, switch, firewall, etc., and that's going to put me on the device that happens to be supplying whatever it is I'm trying to do. So again, I get in my car, I drive to Les Moise, I walk in the store, I find the ski pants, that I want, try them on, make sure they're going to work. I go pay my bill and I go home. Next time I go out to the ski hill, I use them, right? So no different than I'm over here, I've got Bob who's hanging out here, and I've got Sue over here, and I want to send, that's supposed to be an E, not an U, or Sue's hanging out over here, so I send traffic to Sue. Actually, that's the Bob routes this way to reach Sue. Now, the way that it's going to look at it is you're going to see 4.4.4.4, and you're going to see as the router ID, the advertising router, and you're going to see 10.4.4.4.0/24 as a stub network. Now, what's a stub network? We haven't gotten that far into OSPF yet. What's a stub? A stub network is an advertised network that does not have a infrastructure device attached to it. So a stub network is a user subnet. Anything that connects to users. There is the device that's advertising that is the only device that's on that LAN segment. So I'll get more into the other types of networks that are going to be out there, the transient and stuff like that, and how you can. We'll break down the OSPF database at a later point in time once we have stuff built out. But that's essentially what I want you to know about how that comes into play. So I like to use that analogy when I go and explain how EIGRP is the same way. So, and then once you have network layer reachability information, NLRI, and BGP, you're doing the exact same thing. You are saying, okay, who owns this subnet and route to this particular advertising device? The advertising router, or in this case here, the router ID, The router ID is going to be the node that owns the prefix that's physically attached to it. Now, it's not always going to be 100% that case, because when you get into situations like redistribution, so you might have a very large environment, and on the edge of the network, you might have BGP terminating DMVPN connections over whatever WAN connectivity you have to a remote site. And let's say, for example, that you're at a spoke site. That spoke site is running OSPF in the LAN, but over DMVPN, you're running BGP. And then on the HQ side, you're also running OSPF because you don't want to stretch OSPF over DMVPN. I don't recommend using anything but BGP over the WAN. That's a personal preference over after years of doing this. That's just the way that I like to do things. It's a recommendation that I send to all my customers. There's nothing wrong with running OSPF or EIGRP at a base level. You can do it. I'm not saying you can't, but my personal choice as an engineer is to not run an IGP over the WAN. I'll get into that in more detail when we get into WAN connectivity and DMVPN, IPsec VPN, GRE tunnels, all that type of stuff. We'll get more into the design aspects of it, but that's essentially my opinion, if you will, on that. Now, in situations where you've got LAN islands and then a BGP over the WAN, you're going to redistribute OSPF into BGP. BGP is going to take that route, propagate it somewhere else, back to the HQ, for example. The HQ DMVPN device is going to get that, and there's going to be a redistribution rule that says go back from BGP back to OSPF, and then OSPF will take that and propagate it. The interesting thing about that is now your OSPF is inconsistent, meaning that you don't have visibility into another routing protocol at a redistribution point. You are hoping and praying that whoever deployed it did it correctly, and there's no loop, there's no other extraneous configuration pointing you in the wrong direction. You're hoping everything is going to be settled. So when you get into redistribution points, the advertising router will be the router that redistributed. So if I am a BGP and running OSPF at the same time and I receive a route in over the WAN from the spoke, it lands on the hub router and BGP redistributes that into OSPF. Whatever the OSPF router ID is, that's going to be the originating router. That's going to be the originating router ID. And that router ID will propagate the route. Now, what's going to be interesting about that is on the other side of that connection, right? Now you're on the spoke side, receiving traffic from the hub. When you redistribute BGP into OSPF, the router ID at the spoke, that router ID will then be the advertising router, because then it's got to get redistributed. There's got to be some sort of router ID associated to that propagation. And that's going to be how you propagate your routes and how the router ID is going to be. We're going to see this more when we get into how this does things on a large scale. Now, there's a question. What if I have OSPF running over the WAN? Like you said, you can do it. So now OSPF is running over the WAN. What happens then? Well, in that particular case, the router ID, because OSPF now has full visibility of the entire topology, right? You don't have cutoff points in the network. So in those situations, when you have that type of a scenario, whoever the originating router ID is, that information propagates, assuming that you don't have different OSPF processes on the same device. So can you do that? 100%. You can have multiple OSPF processes on the same router and then redistribute between processes. Now, I don't recommend doing that unless you have a specific use case for it, but there are scenarios where it might make sense. Specifically like a DMVPN environment or EIGRP, right? We talked about that before a little bit in scale, right? I don't want to have, when you run into stuck inactives with EIGRP, where you don't want to have like a route in California being learned by Virginia and then propagated over the WAN to the UK and then being somewhere in, say, Belgium or whatever, and you run into stuck inactives because it takes too long to get the query to go from Belgium to California and back to Belgium over the entire US, over the WAN. It's too much of a stretch. Well, in that case here, you'd use a different EIGRP AS for your WAN connectivity. Use a different OSPF process, not a different area, a different process for your WAN connectivity. And again, we'll talk about that more in detail later like I said, we're not going to just say this is what we're going to deploy like we do with Enterprise Lab 1. We're going to put in, rip out, put in, rip out, and play with different things just so you guys get a full picture of how this works. So that's how my brain works. So, but there's a lot of just playing around with stuff. Now, if your OSPF is if you're running the same process ID in every router and it's locally significant, so you don't really care. So you can use the OSPF process 1 everywhere, but it's area breakups that change the OSPF database a little bit. You're injecting type 3 LSAs when you do that, but we'll get to that more in detail when we talk about different area types. But for at the CCNA level, if you decide to run OSPF everywhere, and you can do that, we'll demo out full EIGRP, full BGP, full OSPF, just so you guys can see the stretch of what that would look like. When you do stuff like that, there's technically nothing wrong with it, right? You can do it. It's just not good design. So if you have that situation, whoever owns that router, owns that particular prefix enabled, that particular subnet is on a particular interface on a particular router, that router ID is going to be the owner of that prefix because it's on that device. Then if you have a bunch of OSPF adjacencies and you're consistent across the entire environment with OSPF, when you're doing all this advertisement at the spoke site, the hub is going to see the same router ID. If you were to do a show IP OSPF database and dig into it, the advertising router is going to be 10.1.1.16 or whatever it is that you got it set as, and then you're going to be able to go and dig into that. The advertising router is not going to change unless you start to break up your routing environment to be like a different protocol over the WAN, like for example BGP over the WAN, stuff like that. So these are things that you're going to have to I'm going to demo them for you so you guys can see what they look like, but these are some of the characteristics and capabilities that you're going to have to understand when you start getting into the weeds of how routing works. It's not terribly difficult to understand. It's just one of those things where you just have to go through the steps, the rigmarole, the minutia of how routing works on a large scale. And we'll walk through that just because of the fact that, we're going to be able to. It's not going to just be like, okay, here's how OSPF works. Well, let's demo this particular situation. So hopefully that makes sense. So we have that. So interface IP addresses. So for OSPF version 2, the primary IP address, and then OSPF v3, the interface is the link local address. And so how that would come into play. Or remember I said if the primary IP. So the primary IP address will be the router ID, and OSPF v3, the link local address will be your router ID. Some common OSPF adjacency attributes. The interface area ID, area 0, area 1, area 10, whatever the case might be, and we'll talk more about areas. Let's see. We'll talk more about that down the road. We'll get into what the areas are. An area for right now, until we get further along, an area is nothing more than a flooding domain. That's it. Like EIGRP's autonomous system number is its flooding domain, the OSPF area is the flooding domain for OSPF. The hello and dead interval, and by default, the hello is 10 seconds, the dead interval is 40. So the dead interval is always going to be 4 times the hello. So if you modify the hello, I believe it'll automatically adjust the dead. Interface network address, that must be in the same subnet. Obviously different IPs. Interface MTU should be the same. By default, it's 1500. But if you're going to have one side, it's going to be 1600, the other side is going to be 15. You'll have an MTU issue. Network type, point-to-point versus broadcast. Authentication, whether it's going to be clear text type 0, which is no authentication. Type 1, which is clear text. Type 2, if it's a hashed algorithm, and technically speaking, even encryption is type 2 because it's using a hash. Stub flags. Are you going to be doing a stubby area, a totally stubby area, a not so stubby area, or a totally not so stubby area? And we'll talk about what those are in detail when we get into the different area types and how we can work with those. And then other optional capabilities, like, are you going to allow translation of type 7 to type 5 LSAs? The hello packet. Routers send periodic hellos out OSPF-enabled links every hello interval. The hello packet is a whole bunch of different things kind of wrapped into one. You have the local router ID. Remember I talked about that. That's important to remember because you need to be able to identify yourself. Your area ID, your interface subnet mask, your interface priority. By default on most interfaces it's going to be a priority of 1. Your hello indent interval, your authentication type and password. So are we a clear text password? They were type 1, and then whatever the password is going to be. If you are a broadcast network segment, it's going to be your DR BDR address. Any options, and the router IDs of other neighbors on the link. Remember I said that in the hello packet, when you start talking about two-way, do you see your neighbor router ID in the OSPF hello? If you did, great. If not, that's a problem. Now the adjacency state machine. This is something that I definitely recommend you guys kind of master, because I could totally see Cisco throwing a, hey, do you know how what does two-way mean? Or doing a drag and drop and mix and match. I could totally see Cisco doing something like this. Down is no hellos have been received from your neighbor. Simple enough. Attempt. This is for unicast only. And I haven't talked about unicast at all yet, but let me talk briefly about that. Just like in EIGRP with unicast neighbor relationships, or I say neighbor relationships because they are unicast, they are manually defined. Like BGP, they are appearing, not an adjacency. Appearing, when you use this, means that there is no multicast transport available. So it might be kind of hard for you to wrap your head around that, because you might not even be really familiar with multicast. But out of the gate, multicast works link local between the devices. If you want to route multicast, you have to turn on IPv4 multicast routing. We'll do that at a later point in time. But if you have a transport of whatever type where multicast is not supported, for example, you might have like old school frame relay. If you didn't turn on the broadcast capability on your DLCI, your data link connection identifier, your DLCI, then you would have to set the neighbor command in OSPF in order for the adjacency to form. So you don't have to worry about that no more. Frame relay is a thing of the past. If you want to go check out frame relay, go check out some of my really old videos that I recorded, almost 10 years ago that cover frame relay. But that's why I'm actually re-recording everything, just so that it's up to date and all that good stuff that goes along with that. So then you have the init state. So this is for multicast transport. I received a hello packet from a neighbor, but they have not acknowledged a hello from me. We have two-way. I have received a hello packet from a neighbor, and they have acknowledged a hello from me. Indicated by my router ID in neighbor's hello packet. Remember what I said about router IDs of the neighbors on the link. A list of routers seen on my segment, a list of router IDs the neighbor sees. Issues at this point indicate layer 2 issues. And so this would be, for example, you don't have the right VLAN or the right trunk. The trunk doesn't have the right VLAN allowed. Stuff like that. This is all layer 2. This is direct communication at layer 2 between your devices. So you're talking, if you can't ping across it, that's a bad sign. Exchange start. First step of the actual adjacency. So master and slave relationship is formed where master has a higher router ID. Master chooses the starting sequence numbers of the database descriptor packets that are used to form the actual LSA exchange. So master slave. What exactly does that mean? Master slave is going to be, you have sequence numbers. So you go back and forth. So this is actually before DR BDR, to be honest with you. So this is after DR BDR, because you're a two-way, you're exchanging information back and forth. So the two-way, you're going back and forth, and depending on the scenario, if you have a broadcast network type, you're going to do a DR BDR election. Once that process has been done, DR BDR has been elected, then you'll go into master slave. The master slave is simply for which device is going to choose the sequence numbers that you're going to see, and the sequence number is simply just to make sure that you haven't gotten a duplicate of a particular LSA. That is all the sequence number is for. And the master chooses the sequence number for database packets that are used for the actual LSA exchange. The exchange itself is link local state database is sent through DBD, database descriptor packets, and the sequence number is used for reliable acknowledgement and retransmissions. So if you have stubs and other stuff going on, this is where you're going to run into problems where you, like, one device on a link is, like, you've got router 1. Actually, let me show you the topology. So an example of where a stub would come into play is I want to give this block of routers or switches, I want to set switch 7 and switch 8 would be their default gateway. I'm going to set these guys as the gateways. And if I set the OSPF stub type, whether it's not so stubby area, totally stubby, so on and so forth, in this particular case, then if I said stub on this side but not on this side, when you're going through the exchange, that's where that would pop into play. And just for clarity's sake, if I was going to do a stub type, it would be totally stubby area here. It would be totally stubby area here. It would be totally stubby area here. If I wanted to do a stubby area here, and I would do a not so stubby area in this one, because there's going to be redistribution. So if you want to know the difference between stub and totally stub versus not so stubby and totally stubby, or totally not so stubby, simply means, do I need to do redistribution or not? If I need to do redistribution, automatically NSSA, whether it's not so stubby or totally stubby. And we'll talk about that in more detail later. But that's essentially what you need to keep in the back of your mind. Loading. Link state request packets are sent to ask for more information about a particular LSA. So think of this like you do a full database exchange, then it's been exchanged, then you are going to say, okay, I want to just double check. So you're basically fact checking your neighbor. Do you actually have everything? If you do, great. Then a full resync is happening, and then you go to full. Neighbors are fully adjacent, and databases are synchronized. That's the first step, right? You just formed the adjacencies, right? Or you did a full exchange. Now step 2 comes into play, and step 2 and step 3 are a little less intense because you don't have as many little things to worry about. Once the databases are synchronized, path selection can begin. Each router's LSA includes a cost attribute for each described link. In other words, best path that is lowest end-to-end cost. Best path to a particular destination is based off of the lowest end-to-end cost. Multiple equal cost paths are allowed through equal cost multipath or ECMP. Cisco's implementation uses a bandwidth-based cost, but RFC says you can use whatever you'd like. The default cost out of the gate is going to be 100 megabits per second divided by the link bandwidth. So if you're dealing with a 100 megabit per second interface, you're going to give it a cost of 1. Now, if your link is 10 megabits, well, 10 divided by 100 is going to be 10, right? Now, 100 megabits per second is kind of old at this point in time, right? So what do you do if you've got 10 gig everywhere? Well, the simple answer to that is you're going to use the reference bandwidth command. That's going to bump up your reference for your cost reference from 100 megabits per second to, say, 10 gig or 40 gig or whatever the common link speed is for your particular environment. That's what you're going to do. I believe Nexus goes 40 gig. But you can modify that. And I definitely do recommend that you do that sooner than later because, simple, you want to make sure you're doing accurate cost projections when you're doing your configuration. So I'm going to show you guys how to do that because everything we're running is gigabit. So we're going to be going through and modifying the reference bandwidth, and then I will show you guys how to change the speed and change the cost because you can do it manually as well. You can say IP OSPF cost X, stuff like that. So that's what we're going to play around with that. Now you get into neighbor and topology maintenance for step 3. Is once adjacency is established and the shortest path tree is built. And actually, let me take a moment to talk about what is the shortest path tree. If we talk about shortest path first, what is the shortest path tree? SPT is going to be what is the shortest path from me to you. Simple as that. That's all that means. So you ever gone into a mall or an airport or something like that, and you're like, where am I? So you walk up to the, you know, the map of the mall, if you will, the directory, and it says you are here. And then from there, you look where you want to go, and it tells you, okay, I want to go to Macy's. You know, I want to go buy a new suit, or whatever it might be, or I want to go buy my wife a birthday gift, or whatever. So I'm gonna go look. Oh, there's Macy's on the thing. It is 212 in blue. So I look for the blue section. I look for 212. There's Macy's. Here I am. I'm gonna figure out what the shortest path from me to them is. I have to go up here or make a left. Okay, cool. Simple as that. That's what the shortest path 3 is. So you're going to hear about this in multicast as well. And it means the exact same thing. Shortest path 3. So now you're actually going to hear, you're going to have the source path tree. You're going to hear the shared path tree. So multicast gets a little bit more interesting, but we'll talk more about that in detail later. Now the hello packets are used to track neighbor changes, and then LSA fields used to track topology changes. Hello packets are going to be, is that neighbor up? And then LSA fields are, is there a new topology? Did something happen to it? That type of stuff. Tracking neighbor changes. So hello packets continue to be sent on each OSPF enabled link every hello interval. So 10 seconds by default. 10 seconds or 30 seconds by default depending on the interface type. If the hello is not received from a neighbor within the dead interval, the neighbor is declared down. Default is 4 times the hello interval, and it can be lowered to 1 second for faster conversions. They call it fast hellos, and you can do it even faster nowadays with BFD. So we'll talk a little bit about that in detail when we get there. So there's that. Now the 30-second one here is going to be if you're dealing with NBMA, non-broadcast multi-access, or frame relay. But since we're not going to be dealing with any of that, you can pretend like it doesn't exist anymore. Tracking topology changes. When a new LSA is received, it is checked against the database for changes such as sequence number, used to track new versus old LSAs, the age, used to keep information new and withdraw old information. There is a periodic flooding that occurs every 30 minutes, known as the paranoid update. And then LSAs that reach max age are 60 minutes. And the checksum is used to avoid transmission and memory corruption. Now let me talk a little bit about the paranoid update. So think of this like you have a... no, I don't want to use that analogy. That's not a good one. So what will end up happening is, just to ensure that the network is doing its job, OSPF will automatically reflood the network every 30 minutes, just to make sure that everything is working the way you would expect it to. It's to prevent routing issues in the future. Now, back in the day, there were really slow links, and they're still out there. They're just not as common. And so what they would do is they would use a capability, and I can't remember the name off the top of my head. It was what is the term for that? No, I thought about it as I was talking about it. I'm like, well, what is that? OSPF slow interface. What is the word I'm looking for? There is a term for it. I can't remember what it is off the top of my head. It's not flex links. It's frame relay timer. There's a term for it. I can't remember off the top of my head what it is. The idea here is that you only send an update if there's an update to send. And I can't remember off the top of my head what that thing is. Actually, let me scroll through this real quick. Let's scoot this back over here. I can't remember what the term is because it's been so long. As you can see, I took a lot of notes. So if you are interested in reading these notes, they will be available to you. It's all about authentication. I can't remember what the command is. It was like flood something around flood circuit, flood whatever it is. I can't remember off the top of my head what it is. But is there flood war? It's not that important, but demand circuit. There it is. Demand circuit. Flood reduction. Okay, here it is. I knew I'd find it eventually. So flood circuit, demand circuit would be hellos and refresh of OSPF routing information are suppressed on demand circuits, allowing the underlying data link connections to be closed when not carrying application traffic. And then flood reduction is an LSA's age is never incremented past the value of max age. And this is for very, very slow circuits. Back in the day, the do not age bit would be set. So if you had a scenario like that, that was a particular case where the circuit was super, super slow, like a fractional T1, like a 768, stuff like that, where you would get into those type of situations. I was like, I know they're in here somewhere, but I couldn't remember exactly what the term was. But right here. So that's that. Now LSA flooding. When change is detected, new LSA is generated and flooded out all links. OSPF does not use split horizon. Self-originated LSAs are simply dropped. Not all LSA changes require SPF to recalculate. So link up-down event, rerun versus sequence number change, do not rerun. So if you notice, so a link down event between two routers, that is a rerun of SPF. Where sequence number changes do not rerun SPF. The prefix is still there, the sequence number simply just changed. So OSPF behaves like distance vector between areas, does not have topology visibility and end-to-end between areas. So what this means right here, self-originated LSAs are simply dropped. A self-originated LSA means that you receive your own router ID with the link state advertisement back in, you drop it. Why would I want to learn about something I already own? Simple as that. Or somebody comes knock on your door and be like, hey, did you know this house is not for sale? No kidding. So stuff like that. And then you get into when to run SPF. Like I said, if a transit link between two routers goes down, you're going to want to know about that. Then you're going to rerun SPF to calculate around the failure. Stuff like that. So that is pretty much it for this video. I know it went kind of long, but like I said, it's one of those protocols where I'm very, very well versed in it. So we'll be talking about forming adjacencies in the next video and how we go through the details of that. It's very going to be just like EIGRP, Wireshark debugs, so you guys can see the whole process. But it's basically what it is that you need to know about getting everything stood up. With that being said, everybody, thanks so much for stopping by and hanging out with me in this video. If you haven't already done so, drop a comment in the comment section below if you have any questions, comments, concerns, feedback. Please like, share, and subscribe, and I'll catch all of you fine people in the next video.